Here is an explanation of work energy and momentum notes. Formulas look like this. This is for the potential energy in a spring, where K is the spring constant. Kinetic energy you're familiar with. Momentum, mass times velocity, you're familiar with. Work is force times distance. And if we're dealing with a force that is not exactly in the direction of motion, then we have to factor this in. So this is actually only the component of force that is in the direction of motion times the displacement, or the actual distance that it moves through. And then down here we have two equations for the potential energy. Notice the G's. So the one with which you're familiar is that the potential energy due to gravity is mgh. This is at the surface of Earth. We also have a different equation, which is actually the same thing. This is a specific case of this more general formula. This is potential energy. Notice the big G is like the universal gravitational constant. This looks very similar to the force, gravitational force, except the R isn't squared. So if you were to take the gravitational force, multiply it by R, one of them cancels out and you end up with this for the potential energy due to gravity. We'll talk more about that later. Down here, this is related to momentum. Okay, so what we say is when an object's momentum changes, we call that impulse. Okay, so delta P would be impulse. And this is an equation for the impulsive force. So the force required to change momentum of an object by a certain amount over the course of some time period. Notice how when an object is slowed down over a very small period of time, the force is great. And we'll talk about examples related to that as well. So the work energy theorem, you kind of know that like when work's done on something, it gains energy. Okay. There's a little more detail to it in an AP Physics class. So what we can say is that net work is going to be change in kinetic energy. So you can have an object, for example, that's being lifted. Let's see if I can draw on here. So if you have a box and you're lifting it, okay, and you're lifting it at a constant velocity, gravity's pulling down with the same force. So what we would say is that the net force on this thing is actually 0. Okay? Because you're pulling up with the same force that gravity's pulling down, so the net work on this thing as it moves up at a constant speed is actually 0. Net work would be 0, its change in kinetic energy would be 0. And that's what I have here. So if something's moving at a constant speed, its acceleration is 0, which means its net force is 0, which means the net work would be 0. Now if the question asks something different, such as how much work is done on the object by the person lifting it, then it would simply be that force times the distance it's lifted. And that would be its increase in potential energy. So we say that the person did some positive amount of work, whereas a force due to gravity actually did some negative amount of work, which I know is weird to think about, but that's the way it is. So it's, yeah, okay, we'll talk more about that. Difference between a conservative and non-conservative forces. Conservative force is something like a spring or gravity. Oops. Where was I? Conservative force, something like spring or gravity. So it's associated with increasing potential energy. It has to be something that you can get back and do useful work, such as useful work, think lift something. Okay, so if you had a spring and you compressed that spring, so pushed it down, okay, you've increased the spring's potential energy. That's a conservative force because you set a box on the spring and the spring would push it back up. Something like friction, all right, do I list friction here? So friction is a great example of a non-conservative force. With a non-conservative force, you're not going to be able to get that energy back, essentially. So while in the universe energy is always conserved, okay, the energy available to do useful work is lost, and in general it's due to heat energy. So friction moves up the molecules, or increases the speeds of the molecules in the surfaces, and that heat energy can't be then turned back into lifting a block or something like that. That's it for this one. We'll move on to the next page in a separate lesson.